Welcome back. This will be lecture 22 of EC253C Microprocessors and Microcontrollers. And today we'll be starting our unit 3. In fact, we have already discussed one of the topics that was in unit 3, that's input-output programming. Today we will be discussing about Avrc programming. So far we have done programs in assembly language, and today we'll be moving towards C. The main topics that we will be discussing today, first of all, we will be discussing why is C, why we write programs in C, or maybe or in some other high level language. And then we will also be discussing about a general Embed C program, what's the general structure, general embedded C program. We'll be also discussing about C data types. And then we'll be doing some examples that may involve maybe input-output programming using C and also time delays. We have already done these programs using assembly language programming. Today we will rewrite these programs using embedded C and time delays, how to incorporate time delays using embedded C. And also we'll be discussing about logic operations we use in embedded C, because these logic operations are very necessary for programming in C, particularly for bit manipulation. So the first question here is why C? Why C? We were fine programming in assembly language so what was the need for C? The first thing is, if you remember that if we want to write programs in assembly language, we need to memorize the mnemonics, we need to memorize the exact architecture of a particular microcontroller. In C, programming is more easy, it is easier to write the code. Also, since it's easy, we don't have to remember many things, it's less time consuming. And then once we have written a particular code, a particular program, it's easy to debug, it's easy to modify, it's easy to update. Debugging, modify and update is also easier in C or in any high level language programming. So these are some of the advantages, and in fact you can say this is a single advantage, that it's easier to write the program and therefore less time consuming, and it becomes easy to debug, modify and update the code. We can also say, or one other advantage of C programming or any other high level language programming is that we can use the code in function libraries. Use of function libraries. You may have seen in your C programming that we include many libraries before writing the code, and then we use the functions that are included or that are defined in those libraries, and then we don't need to write the details of those functions. We may see this in our examples later. Also, one other advantage of C programming, embed C programming, is that C code is portable. It can be portable from one microcontroller to another with maybe little or no modification. So that is also an advantage. We might be writing code for maybe at Mega 328 microcontroller, and then on some later date we might want to shift to some other microcontroller. If we were writing in assembly language program, we have to rewrite the entire code. But see, if we write coding in C language, we might have to do some subtle change, and this code might work for the new microcontroller also. These are the advantage, but there's a disadvantage also. That is usually the size of the hex file that is generated when we write the code in C language is larger if we have been writing in assembly language. When we write in assembly language program, we have an assembler that converts, and then a hex converter that ultimately converts this assembly language program into a hex file that is burned, or that's burned actually inside the memory of the microcontroller. In When we write a high level language program, maybe in C, it goes through compiler, and then it goes to assembler and the hex converter, and finally change in the hex file. But the size of this hex file will always be, most of the times, usually it is much larger than the hex file that is generated when we write in assembly language program. Because in here, when we write high level language program, a machine compiler is a machine of software has to change these high level language program into basic instructions, and then those instructions are changed into hex codes. But when we write an assembly language program, the programmer himself takes care of what is the optimal code. So the hex file that is created when we write in when we write in high level language, for example C, is usually large. So that is a possible disadvantage of writing in writing in high level language. But there are many advantages also, like we have discussed. It is easier, less time consuming, modification is easy, we can use code in the function libraries, that's the biggest advantage, and it's also portable. First, before discussing the high level language, let us discuss about whenever we discuss a new language, we discuss about the data types. Or before that, let's discuss about the general embedded program, general structure of an embedded program. I believe all of you have done C programming in your previous semesters. So what's the shape of a general C program? First of all, what is the first statement? In most of the programs, we include some files. Maybe we write something like this, #include. Then there is something. These may be more than one statement. And then we start our program with void main, the main program. Inside So a general C program has got three regions: region 1, region 2, then there is region 3. Where is the main program? The instructions that are actually executed, that means they are in the region 2. Region 2 contains the main program. What we do in region 1? Maybe global variable declaration, maybe including these files, etc., these things. So, and then there is region 3. What's the purpose of region 3? What we do in we define functions. If we have used, also in region 1 goes the function prototypes. So maybe region 1 we include files, include libraries like standard input output, console input output libraries, and also we define global variables, and also maybe functions. If we have used any function inside the main program, the function prototype we write here. So function prototype, and there may be some other things also. Region 2 main program goes there. In region 3 what we do, we define these functions. Function prototype goes in region 1. We use functions inside the main program, and the functions are defined. Whatever functions we use which are not included in the libraries, the functions defined by the programmer. Those functions are defined here. Function definition, that means the code inside the functions is written here. This is the structure of a general C program. The structure of an embedded C program varies slightly from the general program. Let me write it here. Hash include. Again, we will start by including some libraries. There will be a region 1. Then we will start with void main. Then we have another region, that's known as region 2. After that we have an infinite while loop. We can implement this infinite loop, not infinite while loop but infinite loop, using any loop. So the simplest thing is writing something like this, while 1, because 1 always returns true, so this loop will continue to run. Then we close this loop, we close the main program, and then we have the region 4. So basically, in an embedded C program, in a typical embedded C program, we usually have 4 different regions. We have region 1 here before the main program, and then we have region 2 that's inside the main program but outside the infinite loop, and then there is region 3 inside the main program and inside the infinite while loop. Then we have region 4. Region 1 will again be same. It will include it will be used to include libraries, global variable declarations, function prototypes, other things. Region 3 and region 4 here in embed C program will be similar to region 3 of the general C program. It will be used to define functions. The main program here will go in region 3, because in Embed C, as I have explained in previous lectures, we need to run the code. We always need to run the code. The code should be running always, because in the embedded system, inputs can come anytime. So at that time the code should be running. It should check the inputs and give a specific output. That's why we use an infinite loop to keep the program running always. And then there is a region 2. Some of the things we don't need to run always, like port configuration, like defining variables. We need to run them, or we need to execute them only once. For example, defining a particular port as input or as output, that needs to be done only once in a program. So those things go in region 2, like port configuration. That means configuring a port as input or as output. It only needs to be done once. Checking inputs, the embedded system needs to do it again and again. So we keep that in region 3. In region 2, we keep those things which are inside the main program but need to be executed only once, like port configuration or maybe variable declaration. This will be more clear when we write some programs or when we do some examples. Okay, so that's it. Embed C program. A typical embed C program usually has 4 regions. Region 1 is used for the same things, including libraries, global variable declaration, function prototypes, other things. Region 2 are those things which go inside the main program but are executed only once, like configuring the port as input or output, variable declaration, and other things. In region 3, we write our main program which needs to be executed again and again in an embedded system. And then region 4, we define our functions. Any function that has been used in region 3, we define in region 4. So that's it, the general C program. Now, before discussing any language, what's the first thing we discuss? We discuss about the data types that are used in that language. So what are the data types used in embedded C? Data types. These are more or less similar to the data types used in general C. Like we have here, we have unsigned char, or we have char also. We also have unsigned and signed int here, and int. So you may be knowing that the char is a 8-bit wide data type and int is a 16-bit wide data type. Apart from this, we also have unsigned long and long, that's a 32-bit wide data type. And we also have float and double that are used for floating numbers. They are 32-bit wide also. The first thing is, what's the most common choice in ATmega 328 microcontrollers? What's the most common choice of the data type which needs to be used? Since ATmega 328 is an 8-bit microcontroller, that means it has an 8-bit data bus. It also has an 8-bit arithmetic logic unit. So it works on 8-bit data. Therefore, the most common choice of the data type in an ATmega 328 microcontroller is char, either unsigned char or signed char. Both are 8 bits wide. Since unsigned char, the MSB is not used for sign, so range goes from 0 to 255. I believe you have read these things, studied these things in your C programming course. In char, the range goes from the MSB, the 8th bit is used for sign bit, therefore we only have 7 bits for data. Therefore range goes from -127 to 127. Similarly, in an unsigned int, range is from this is a 16-bit data type, range will from 0 to FFFF, or 0 to 1111, 1111, 1111, 1111, 16 ones, that is 65535. And also in a signed int, by default, if we write char or we write int, most of the compilers treat them as signed. So if we write simple char, it means signed char. If we write simple int, it means signed int. So signed int will be from -32768 up to +32767. Similarly, we have long, that's 32 bits long, and then we have float and double, they are also 32 bits. So let's do an example. Let's rewrite a code that we have already done in assembly language program. Let's assume that we have a microcontroller, ATmega 328 microcontroller. We have connected LEDs to port B. So there are 8 LEDs to each pin of port B. So what's our aim here? We need to turn on these LEDs, turn on, and then we need to turn them off again, and we need to repeat this cycle. Okay, so we have done this program in assembly language program. What we did, first of all, we configured the ports as output port using DDR B register, because we are dealing with port B. We configured the ports as output port, and then we write a number on these ports that turns the LEDs on. That number is 1111 1111, and then we give a brief delay, and after the delay we turn the LEDs on by sending a 0 or 0 volts to all these pins. That's by writing a number 00000000. Then again some delay, then repeating the cycle. Simple. So let's try to write this code in an assembly language in C. The first line, the first statement that we have to write is #include avr/io.h. This library will actually include all the input output details, the internal configuration details of the AVR microcontroller. So this is necessary. Then I will start with my main program. You can write wide main or int main, anything, int main, but then you have to return something, int main, and we don't have to pass any value to this, so we can write wide, or we can skip this wide also. we don't need to write it next. It depends actually on the compiler. Let's skip that for a while. Into main. So here goes my main program. So what's my main program? First of all, I have to configure the port. Which port? Port B, because I'm using port B as output port. And how do I configure port B as output port? There's a register associated with port B, that is DDRB register. I write ones to that register. And you may be remembering how we write ones in an assembly language program using in and out statements. Here we simply assign that value. So I will simply write DDRB equal to 0. So DDRB will get 0. Or if I need to write this number in hex, I have to write 0x00. It's one and the same thing. DDRB equal to 0. That means 0 is assigned to DDRB. DDRB is the port configuring register associated with port B. Data direction register associated with port B. So this statement, when it will get executed, it will actually configure the port B as input port, because I'm writing zeros. But since I have to configure it, I have to configure it as output port. So I need to write ones. So I can simply write 8 ones. That means I can write 1 in binary 1 1 1 1 1 1 1 1. But since this is binary, I need to put 0B before it. So DDRB equal to 0B 1 1 1 1 1 1 1 1, or 1 1 1 1 1 1 1 1 means 255 decimal. So I can simply write DDRB equal to 255. Or if I need to write in hex, which is the usual way of writing, this usual style of writing, we usually write in hex. So I need to convert this number in hex. 255 means 1 1 1 1 1 1 1 1. That means FF in hex. So I can simply write but I have to put 0x now for hex FF. So this instruction will actually configure the port as output port. Then what I need to do, I need to put an infinite loop. This infinite loop is different than the one I talked in the general structure of the Embed C program. I will explain that later. What's the difference? This infinite loop I am putting here because I need to turn on and off the LEDs infinitely. The infinite loop I was discussing earlier, that's used when we need to get data from the environment. We'll discuss that later. For now, when I write and inside the loop, I have to turn the LED on and off regularly with some delay. So what I can do, I can write port B. I will turn on the LEDs by sending ones to each pins. That means I will write 0xFF. Then I have to write some statements which will cause delay. We are not discussing those statements yet because there are more than one, there are a couple of ways or more than 2 ways to actually incorporate this delay in C programming. So let's keep it there for some time. Then after some time I have to turn off these LEDs. Port B. So how I will turn? By writing zeros. Again, you should remember that port B equal to 0 is similar to port B equal to 0B0 is similar to port B equal to 0x00. Similarly, port B equal to 0 cross FF is similar to port B equal to 255. Then again, there will be some delay. And this program will repeat. So it's a simple program. I'm including an AVR IO file that will include the input output dates and other things. Then inside the main program, I am first configuring the port by writing ones to DDRB as output port, port B as output port. Then I am turning on these LEDs connected to port B by sending ones to port B, and then some delay, and then I am turning them off, again some delay, and repeating this thing, turning on and off, and this will go forever. This is a simple example how we write some data to the ports, and that to the byte size data. We have not yet discussed the bit addressability of the ports. How do we get the data from the ports? Simply by reading pin B register. We'll discuss that after some time. Maybe we'll discuss some examples in the Zoom session. Now the thing is, first we should discuss how to incorporate this delay in a C program. There are three ways. The first one we have used in earlier programs also, by writing some statements that don't have any meaning, that don't do anything. Some statements that don't do anything but just utilize CPU time, and thus the delay gets incorporated. The simplest way here to do that is using a for loop. So using a for loop, we will discuss that how to use a for loop for incorporating delay. Or one of the advantages of the C program, as I have discussed earlier, is to use the functions, the code in the libraries. So we can use the predefined C functions. You should remember that which function to use depends actually on the compiler. And then we also have to include the files that contain these functions. So predefined C functions can be used to incorporate delay, or we can also use AVR timers. We have not discussed timers yet. We'll discuss it in next class, or maybe after that. So first we will discuss how to incorporate this delay using a simple loop. Then we will discuss how to incorporate this delay using predefined C functions. So let me rewrite this program. The first statement goes like this. The first statement is fine. Hash include avr io.h, avr io.h. Then I am starting my main program. I can write void main or int main. It actually depends on the compiler. If I write int main, I have to include one more statement here. That's the return statement. I have to write return 0 here. Actually not return anything. That's why, because int means it's returning an integer value. So I am returning 0. It doesn't have any significance. So after that I can start with int main. Again int main. First I will configuring the port as output port ddrb. Equal to 0 cross ff. Then I'm turning the LEDs all on and off infinitely while 1. I have to turn them off first, on first, or maybe off first, doesn't matter. So I have to write something to port register of B, port B equal to 0 cross ff. Then how to incorporate the delay? As I said, I will write some code, some statements which don't have any meaning. For example, if I write something like this: for I equal to 0, I less than 100, I plus plus, and I don't write anything inside it. So the program or the compiler or the machine microcontroller will run these instructions 100 times. but there's nothing inside it. It will only check the condition. The first time it will check, I will be 0, I will be less than 100, so it will go inside, there will be nothing inside. It will come back, increment this, again check, again the condition is satisfied, so it will go inside, there's nothing inside, again the condition will check, and this thing will be repeated 100 times, and time will be lost in checking and also in increment, and that time can be utilized, or that time, and that way the delay is incorporated. So for that I have to declare a variable here. So I have to write these statements. For that I have to declare a variable. I have to declare a variable I, or maybe any other variable. So I can simply write char x, but that will then I can assign a maximum value of 255 to that. Let me try that. For example, I write char I. So here, after declaring, turning the LEDs on, I will write a loop for I equal to 0, I less than 255, because the maximum value that can be assigned to char is 255, I plus plus, and then since I don't have to write anything inside the loop, I can simply put a terminator. Usually there's not a terminator at the end of the for statement, but if I put a terminator at the end of the for statement, that itself means there's nothing inside the for loop that needs to be executed. So the controller, the processor, will only check the condition and go on incrementing this until the condition is not satisfied, and it will move on to execute the next instruction. What will be the next instruction? Again, I will be now turning off the LEDs connected to port B. Again, I will be writing this for loop. Again, I will be assigning 0 to it, I less than 255, I plus plus, and closing the while loop and closing the main function. So this is the one thing how I can incorporate delays, because this for loop will run 255 times, and some time may be utilized, or some time may be wasted during the execution of this for loop 255 times, and we will get delay. What's the exact delay we will be getting? That's very hard to calculate, in fact impossible to calculate in a high level language. In assembly language we calculated the exact delay. In high level language that is impossible to calculate. So what's the method here? Usually we write the program, burn it, then to measure the exact time delay we use an oscilloscope at the pins of microcontroller. Because the accuracy of delay, there are many factors that will actually define the accuracy, that will actually define the time period of the delay. One of the things is the crystal frequency. We have a hold on that, we know what's the crystal frequency. Second thing is the number of the times this loop is running. That's also that we also know. The third thing that this delay, the time delay, will depend on is the compiler, because the compiler will change this for loop in to the assembly language instructions, and then it will convert it to the hex file. So while converting this the assembly language program, we don't know what type of assembly language instructions this statement gets changed to. It may be different each time, and it may also vary from compiler to compiler, depending upon how good or how accurate or how good our compiler is. The delay will vary. So the only way to know or to measure the exact time delay, when we have incorporated time delays using these for loops for loops, is to measure the exact time delay using an oscilloscope. So this is the first method. The second method is predefined C functions. One thing before that I want to tell you that this is a statement which is used twice. Maybe it may be used more than twice also. So we can create a function, a self programmer defined function that can be written somewhere else, and then we only need to call this function. For example, I can write this program as everything remains same. The first statement will be again hash include avr slash io.h. then I will start writing int main. I won't be defining this, simply ddrb equal to 0 cross ff, then while one. Inside the while one, I will turn on the LEDs by writing ones, and then I will call a function. Maybe I will name that function my delay. And my delay, I am calling that function. Then I am turning off the LEDs, again calling that function, then closing the infinite while loop so that this code gets executed again and again. And then there is, I will close the main loop also. Then I have to define the function, this my delay function. So I will write my delay here and define it. What's the code inside it? I have to declare a variable I, and then I am writing for I equal to 0, I less than 255, and I plus plus. That's it. So this is, or I have to write void my delay because not returning anything, void my delay. This is the function. After that, but I have to put the function prototype here also. So the function prototype goes like something like this: void my delay, the name of the function, in the parentheses. So this is it. This is the same program. I am turning LEDs on and off and incorporating a delay between on and off so that I can visualize it. I don't know what is the exact time period of this delay, that we'll discuss later. And then I wrote this program by defining a function my delay, and then that I am defining here. Simple. Now moving on to the second thing, how to use predefined C functions. Is there a predefined C function? Let's start with this delay. There's a predefined C function inside a particular library that we can use to incorporate that delay, and we also know that that delay is actually measured, so we know what is the exact amount of the time delay we are incorporating. So how to do that? First thing, for that you need to know that these library functions, they vary from compiler to compiler, so you need to check your compiler. The most commonly used compiler, at least here, we use Atmel Studio. Atmel Studio, we have some predefined functions that are used to incorporate time delays. One of those functions is underscore delay underscore ms. This gives delays in milliseconds. We can write any number in the brackets, for example 100. So if I write this function, if I call this function, it's already been defined, I don't need to define it. It will actually incorporate a delay of 100 milliseconds given I have a particular value of crystal frequency attached to my microcontroller, and that value is 16 megahertz. Because as I have already told you that the delay not only depends upon the number of instructions that needs to be executed, it also depends upon the crystal frequency, because that will actually govern the time period of the machine cycle. If the crystal frequency is 8 megahertz, that means our system is slower, so same number of instructions will take double amount of time. So if our crystal, so we need to define the crystal frequency first before writing this delay ms. We need to tell the compiler what is my crystal frequency, what crystal frequency I am going to use. Then the delay will be accordingly. Whatever the crystal frequency I will choose, my compiler will adjust accordingly. My compiler will adjust this function accordingly. So it's not necessary that the crystal should be 16 megahertz or 8 megahertz. It can be anything, but I need to tell that to the compiler. So how we do that? Let me again write the earlier program, rewrite the earlier program. Again starting with hash include avr /io.h. Okay, this is the first statement. Good. And then I need to include one more library in which this delay function is defined, and that is hash include /delay delay/delay.h. I need to include this library because my delay function _delay_ms has been defined in this library only. And also, as I told you, I need to tell my CPU, I need to tell my compiler what crystal frequency I will be using in the hardware. So again, that is not inside the main program, that goes here. I will write statement hash define. I will define crystal frequency f CPU, frequency of CPU f underscore CPU, as if I be using 16 megahertz crystal, which is the most commonly used 16 megahertz crystal with these Atmega 328 microcontrollers. So I write 16 megahertz, that means 16 and 6 zeros. And then I will be starting my main program, maybe int main. And inside the main program, what I have to do, first of all configure the port as output port. So ddrb equal to 0 cross ff, and then the infinite loop while 1, turning on the LEDs, port B equal to 0 cross ff, and then I will be calling this function. How do I call this function? Underscore delay underscore ms, and I will give the delay. Since the delay is in milliseconds, if I need 1 second delay, what I will write? I will write 1000. Then turning off these LEDs. Again calling this function. If I again need a delay of 1 second, I will again say delay ms 1000. If I need 2 second delay, I will write 2 seconds. I am turning the LEDs on. I am keeping them on for 1 second. I am turning them off. Now I can keep them off maybe for half a second also. So I will write underscore delay ms, only 500 here, and then close. I need not to define this delay ms because it has already been defined in util delay.h. So what's happening here? I'm including these files. I'm telling my compiler that the crystal frequency I'll be using later in my hardware is 16 megahertz. then inside the main program, which actually gets translated to the assembly language program, and then the hex file is this. I'm configuring the port as output port, good, and then I'm turning the LEDs on, that are actually sending ones to, I don't know, I might not know what is on my pins. This time we have assumed that there are LEDs, so I'm sending actually ones to all the pins of port B. Then then this voltage or this or if there are LEDs, they will be kept on for 1 second, and then they are turned off and kept off for half a second, and the process is repeated. On for 1 second, off for half a second, process is repeated. This is the program. The third way of incorporating time delays inside, or the sorry, it's the second way of incorporating time delays inside an embedded C program. The third way is using AVR timers, that we will discuss in some other lecture when we discuss timers. The only thing you need to remember here, that there are many functions we can incorporate delay. One of them is delay ms. It incorporates delays in microseconds, and you need to remember that these functions are compiler specific, and this time we have assumed that we are using HTML Studio. If we are using some other compiler, we need to use some other function maybe. Okay, that's it. And then we have also done how to write data to the input and output pins by simply assigning a value to them. The next question is about the bit size input output, the bit addressability of the ports. Because we know that the ports and the registers associated with them are bit addressable. We have discussed that in our previous lecture. So how we actually manipulate the individual bits in embedded C? So bit size IO, bit addressability. Because as we have discussed earlier, that sometimes we need to change the status of individual bits, or we need to read the status of individual bits without disturbing other bits of the same pin. For example, we might have a microcontroller or embedded system where different things are connected to the port B, and an LED is connected to the maybe port B, pin 5 of port B. So what we do, how we manipulate this pin? Again, in high level language we have seen how to do this in assembly language programming. In high level language, this thing actually depends upon the compiler. Some compilers support bit addressability, some compilers don't support bit addressability, and most notably HTML Studio doesn't support bit addressability. So how we actually, what do I mean when I say HTML Studio or some other compilers don't support bit addressability? Means that there are not instructions that can be directly used to manipulate the individual bits of a port without disturbing some other bits in HTML Studio and in some other in some other compilers also. In some compilers we have statements like this. If we need to manipulate individual bits, write to individual bits, we write, for example, something like this: port B dot 5 equal to 1 or maybe equal to 0. If I write port B dot 5, that means fifth pin of port B will be given 1, that's 5 volts, and if there is an LED connected to that, it will turn on. But HTML Studio is the most commonly used compiler, which the compiler we are going to use also doesn't support this bit addressability. So there are alternate methods how to bit address particular ports, how to manipulate individual bits, how to read individual bits, how to modify individual bits of ports without disturbing other bits of that port in HTML Studio. In assembly language, in embedded C using HTML Studio, we use bitwise operators, bitwise and bitwise or and other bitwise operators to access individual bits. How do we do that? We before actually discussing exactly how we modify individual bits using these bitwise operators and or and other bitwise operators, they are different from the normal logical operators. We will discuss that. Before actually discussing how they modify individual bits, we will be discussing what they are. What are bitwise operators? We have studied about the logical operators. What are logical operators? Like we have discussed about AND, logical operator AND. It logically operates, and the symbol here is and. You might have studied this thing in C or maybe in some other courses also. It has two operands, maybe operand X and Y, and if both the operands, if one of the operands is 0, the result is 0, otherwise the result always will be 1. Similarly, the OR logical operator symbol is 1. It also has got two operators, and if one of the it also has got two operands, not operators. Operator is OR, logical OR, and it also has got two operands X and Y. If one of the operands is 1, the result is 1. And similarly, we have an operator NOT, that's a urinary operator. That means it only has a single operand, and it actually complements that operand. If the operand is non-zero, it will convert it into 0. The result will be 0. And if the operand is 0, it will convert it into a non-zero number. Bitwise operators are slightly different. For example, here, if the X is equal to 0 into 32, hex number 32, and Y is 0 cross maybe 42. If I logically AND these two numbers, the result will be all ones, because this is no, it will return a 1 actually. But bitwise operators are different. Bitwise operators. We have 6 bitwise operators in Embed C for Atmega 312 microcontroller. In fact, for other microcontrollers also, we have an AND, we have a bitwise OR, we have a bitwise XOR, and we also have a bitwise inverter. Apart from these two, we also have shift right and shift left. We'll be discussing shift right and shift left later. So bitwise AND, the symbol is a single AND. Similarly, for the single line inverter, and these bitwise operators actually operate on individual bits. For example, if I write a statement 0 cross 35 and 0 cross maybe 40, what will happen? The individual bits will be ANDed, and then we will have a result. That means, for example, we have 35 and 40. We are bitwise ANDing these two numbers. What will be the result? What is 3? 3 is 0 0 1 1. What's 5? 5 is 0 1 0 1. What is 40? It's 0 1 0 0 0 0 0 0. So the individual corresponding bits of these two numbers will be ANDed. So result will be 1 0 0 0 0 0 1 0 1 1 0 0 0 0 0 0 0. So it will be equal to 0 cross 0 0. Let's take another example. We have 0 cross 3 5 and 0 cross F3. What will happen here? Again, 3 5 is 0 0 1 1, 0 1 0 1, and F3 is 1 1 1 1, 0 1 0 0 1 1. Is that 3? Yes. So the result here will be, after bitwise ANDing these two numbers, the result will be 1 0 0 0 1 1 0 0. So the result will be 1 1, that is 3 1. Are you getting the idea how bitwise AND is different from the logical AND? Similarly, for bitwise OR, let's take an example. let's have two numbers. Maybe again we have 0 cross F3. I'm ORing with it, bitwise ORing with another number, maybe 0 cross 0, maybe F. So what will happen? F will be 1 1 1 1, 3 will be 0 0 1 1, and 0 F will be 0 0 0 0, and F will be 1 1 1 was. So individual ORing means 1 1 1 1 1 1 1 1. So the result will be FF. Similarly, we can take another example. We can take some more examples also. Similar things will happen with XOR. For example, I will take an example 0 cross 5 4. Bitwise XORing it with some other number, maybe 3 8. So what will happen? 5 4 means 1 0 1 0 1 0 0. 3 8 means 0 1 1 0. 8 is again it is 1 0 0 0. So ORing means 0 and 0 will give me, if the numbers are equal it will give 0, if they are different it will give 1. So it will be 0 0 1 1 1 1 0 0. So I will get 1 1, it's 3 in hex 3, and this is 8 8 9 and 12. 12 means it's 12. 12 means ABC. Similarly, if I have a number, I am doing 0 cross inverting, bitwise inverting 55, individual bits will be complemented. So 55 was 0 1 0 1 0 1 0 1. I will get 1 0 1 0 1 0 1 0. That's equal to AA because it's 10 10. Okay. So how are these operators, these bitwise operators, used to set and clear individual bits? Clearing of bits, individual bits, using these bitwise operators. You should first remember that for setting the bits, that means writing once, there are only two things: writing once or writing 0. For setting the bits, we use OR, bitwise OR. How we use that, we will discuss that in a moment. And for clearing the bits, we use bitwise and also for toggling the bits, for directly toggling, making 0 ones and 1 0, we use bitwise XOR. Okay, that's fine for now. So how do we use that? You must remember that the OR, how does the truth table of OR look like? 0 0 gives me 0, 0 1 gives me 1, 1 0 gives me 1, 1 1 also gives me 1. Observing it, we must know that the result, if one of the bits is 1, or I can say like this, anything ORed with 1 results in 1. I am ORing 1 with 1, the result is 1. I am ORing 0 with 1, result is 1. So anything, it might be 0 or 1, because anything means 0 or 1 in binary only. We don't have any other thing. So it doesn't matter what I OR with 1, I will always get 1. So anything ORed with 1 results in 1, and anything ORed with 0 or with 0. If I OR 0 with 0, the result is 0. If I OR 1 with 0, the result is 1. That means if one of the bits is 0, the result is the other bit, that there is no change. That means anything ORed with 0 doesn't change, no change. Similarly, so this we can use to set an individual bit. For example, if we have a port, we need to set third bit of a particular port without altering other bits. I can simply write port B equal to port B, bitwise ORing it with a number. What number that will be? For example, I don't have to alter any of the bits. This is the first 0th bit, first bit 0, 1, 2, 3, 4, 5, 6, 7, 8. I have to change only this bit, so I don't have to change these bits. So I have to set this bit, so I will OR this port with a number that doesn't change the states of these bits. What doesn't changes the states of these bits is 0, so I will OR with it 0 0 0 0 0 0 0 0 0, but I have to set this bit, so I will put a 1 here. So I will OR it with a number 0x or 0b, sorry, because I have to write in binary. I can also write, I can change this number in hex and write in hex. 0b 0 0 0 0 0 1, sorry, 0 0 0 0 1 0 0 0 1 0 0 0. Okay, fine. So what will happen here? I don't know what was the states of port B, the pins of port B before changing it, but when I execute this statement, what will happen? Whatever was on the 0th pin of port B, whatever was, maybe it was 0 or 1, will remain whatever it was. There will be no change because I am ORing it with 0. Also, similarly, pin 1, pin 2, pin 4, 5, 6, 7, 8 will not get changed. So whatever was on these pins will remain like that. But pin number 3, I will write 1 to that because I am ORing whatever was at pin 3 with 1. It will give me 1 irrespective of what was on pin 3. So basically this statement is equivalent to set bit. How do I write it? Set bit port B3. I'm setting the third pin of port B. I need to recheck this, the exact syntax of this statement. We have discussed in last lecture. Something like this. I'm setting the third pin of port B without disturbing the other pins. So this is how I actually set a particular bit without changing other bits. And how do I clear? That means write a 0 to a particular bit without changing other bits. That I will do using AND, because if you observe the truth table of AND, sorry, this is bitwise AND. 0 0 will give me 0, 0 1 will also give me 0, 1 0 will give me 0, and 1 1 will give me 0. So if I AND with 1, anything ANDed with 1 doesn't change, because I am sorry, 1 1 will give me 1. So if I AND with 1, the result will be 1. If I AND with 0, the result will be 0. That means anything ANDed with 1 doesn't change. Anything ANDed with 1 doesn't change. But anything ANDed with 0, that may be 1 or 0, is clear. That means a 0 is written, because if I AND 1 with 0, I will get 0. If I AND 1 with 0, I am getting 0. So whenever I have to write 0 to a particular bit without changing the status of other bits, I AND that bit with 0 and AND all the other bits with 1. So for example, if I had to clear this bit, what I will be doing? I will be writing port B equal to port B logical AND with a number 0B 0000, sorry, logical AND with number 1 1, because I don't have to change other bits. How other bits won't be changing? By ANDing them with 1 1 1 1, 0 1 1 1 1 1. So these 7 bits won't change because I'm ANDing them with 1, but this one bit, that's the third bit, will actually be cleared. Similarly, I can toggle bits using XOR, because we know that zeros for the XOR to table 0 0 is 0, 1 1 is also 0, 0 1 is 1, 1 0 is 1. So anything you can observe from the table, that anything XORed with 1, anything XORed with 1, I am XORing 0 with 1, 0 with 1. So the result is the complement of this one. I am XORing 1 with 1, again the result is complementing this one. So anything XORing with 1 actually complements that anything, whatever that anything is. And also anything XORing with 0, anything XORing with 0, if I XOR 1 with 0, the result is 1. XOR 0 with 0, the result is 0. Anything XOR with 0, result will be unchanged. The result will be that anything, that second bit actually. So this can be used as toggling. You can do some examples of how this can be used in toggles. We'll be doing many examples in our Zoom discussion, inshallah, and that will clear a lot of these concepts. Before wrapping this up, let me discuss the bitwise shift operations. We have left shift and right shift. Examples again, examples will be done in Zoom sessions. So what's the right shift? If I write something like this, 0B, it's number 0 0 0 1 0 0 0 0, and then the right shift symbol is this, 2 greater than signs, and then I can put some other number here. For example, I am putting 3. So what will this statement do? This will actually shift all the bits to the right by 3. Everyone will be shifted 3 places to right, and 3 zeros will be inserted from the left hand side. So first these 3 bits will be discarded. So I will get this bit will be shifted 3 places right. Here it will be 0, this will be here 1, this will be here 0 0, similarly 0 0 and 3 zeros. No, this is the number, this is the result. Similarly in left shift, I can write, if I have same number and I am left shifting everything, I will be using less than signs, twice the less than sign used for left shift 3. So every bit will get shifted left to 3 places. So the result will be 0B. Oh, again one thing, 1 2 3, 1 2 3, it will be shifted left thrice. Since every bit will be shifted left thrice, so these 3 bits will no longer be there, so we'll get 0 0 0 0 0 0 0, 8 zeros. We'll be discussing these things in more detail, how we use these bitwise operators, and then this left shift and right shift by reading data from the outside the world, the individual bits, and then modifying them, or also for checking the status, whether a particular bit is high or whether a bit is low, and also then changing the status of individual bits without modifying the rest of the port. That's it for today's lecture. Thank you.